$1.5 billion Starliner, one of the few reusable spacecraft that can carry around 5 to 7 crew members along with cargo. Unlike its counterparts such as Musk's SpaceX Dragon or the Russian Soyuz, the Starliner is designed to land on solid ground rather than in the ocean. It accomplishes this by deploying a combination of drop parachutes, then releasing the main chute and finally deploying airbags to land on hard surfaces, cushioning the hard landings. Let's also take a quick look at the thruster problems that has been delaying its return back to Earth. One issue involves the reaction control system, specifically helium leaks. But why is helium so important? Helium, an inert gas, is used to pressurize the propellants that feed the thrusters. If too much helium is lost, the thrusters may not function properly, which could be critical during the flight, particularly in the capsule's propulsion system. And step-by-step video of its launching stages and re-entry all in the videos ahead. Let's take a look at the basic height comparison between various space vehicles, including an average human, to help us understand the scale better. The Boeing Starliner has a height of around 5 meters, which translates to approximately 16.5 feet. Its diameter is around 4.56 meters, or roughly 15 feet. To put this into perspective, imagine an F-150 pickup truck next to it. For further comparison, we can place the SpaceX Crew Dragon and the Russian Soyuz spacecraft beside the Boeing Starliner. Interestingly, the Starliner weighs a staggering 978,924 pounds, which translates to around 44,000 kilograms when fully fueled for launch. To give you an idea of how heavy this is, consider this school bus, which weighs around 36,000 pounds. This means the Starliner's weight is equivalent to almost 27 buses. That's a tremendous amount of weight, as it is much smaller than its counterpart. The spacecraft's full name is Starliner CST-100. CST stands for Crew Space Transportation, and 100 refers to the Kármán line, the official boundary of space 100 kilometers above the Earth. The vehicle comprises 2 main parts, which are attached to each other from launch until shortly before re-entry. A service module, which provides power and propulsion. A reusable crew module that carries the astronauts inside. Let's take a look at this spacecraft. It has a hatch and a forward heat shield. Heat shields can be thought of as the first line of defense for a spacecraft during re-entry. During descent, an immense amount of kinetic energy is generated. Heat shields help safely dissipate this energy, preventing extreme overheating that would result in structural damage. Inside the heat shield is the important docking arm. When a spacecraft is near the space station, it uses the NASA docking system to access the space station. Just below are the parachute cover modules. When descending at high speed, these deploy to slow the spacecraft down, preventing a crash and ensuring a safe landing. The Boeing Starliner features a clamshell design that allows for easy hardware installation, as shown in this visualization. It also has a flexible cabin design that accommodates a mix of crew and cargo. You'll find seating for up to 5 crew members, arranged in this angle, along with space for the equivalent of 2 crew members' worth of cargo and supplies needed for the space stations. Next to the seating area are the fuel tanks necessary for the thrusters located throughout the spacecraft. These tanks can also store oxygen for the 7 astronauts. Nearby, the cooling systems, possibly including air conditioning units, help manage the spacecraft's temperature during re-entry. Stage 1. Liftoff. The mission begins with the Atlas V rocket lifting off from the launch pad, powered by all its engines. Stage 2. Approximately 2 minutes and 40 seconds into the flight, the solid rocket boosters are jettisoned. These boosters provide additional thrust during the initial phase of the ascent and are discarded once their fuel is depleted, reducing weight and allowing the rocket to continue its climb. At stage 3, around 4 minutes and 30 seconds, the Atlas V rocket's first stage separates from the Centaur upper stage. This separation is a critical step to shed the spent first stage. Stage 4, ascent cover jettison. Following the separation, the ascent cover, which protects the spacecraft during the initial phases of the launch, is jettisoned. At stage 5, approximately 4 minutes and 45 seconds, the Centaur upper stage ignites its engine. This stage provides the necessary propulsion to carry the spacecraft into a preliminary orbit around the Earth. Around 5 minutes and 5 seconds into the flight, that is stage 6, the aeroskirt is jettisoned. The aeroskirt helps to stabilize the vehicle during the early phase of ascent through the atmosphere and is no longer needed once in the thinner upper atmosphere. Stage 7. Centaur Main Engine Cutoff. At about 12 minutes into the mission, the main engine of the Centaur upper stage shuts down. This marks the completion of the powered ascent and places the spacecraft into a temporary orbit. Stage 8. Coast Phase. After engine cutoff, the spacecraft enters a coast phase, where it drifts in orbit for about 15 minutes. During this time, it prepares for the final maneuvers required to achieve a stable orbit. Stage 9. Orbital Insertion. The final stage involves the precise maneuvering of the spacecraft to achieve its intended orbit, known as orbital insertion. Once in the correct orbit, the Starliner can begin its journey to rendezvous with the International Space Station. These are the 9 stages of the Atlas and Boeing Starliner spacecraft required to reach orbit and safely dock at the space station. Moving further ahead, we can divide the reusable capsule into several sections. This section is the crew module, and just below is the service module. Here is the window, and just beside it is the side hatch that can be opened all the way to this angle. Just beside it are the thrusters, which we can divide into 4 stages or parts. Stage 1 is the crew module engines. The Starliner will use 12 reaction control system thrusters to orient itself during atmospheric re-entry. Stage 2 is the service module orbital maneuvering and attitude control engines. Each Starliner will be equipped with 20 engines that generate 1,500 pounds of thrust each to support orbital maneuvers. Stage 3 are the reaction control system RCS engines on the Starliner service module. Each generates 100 pounds of thrust and will be used for on-orbit maneuvering. They will also provide attitude control in the event of a high-altitude abort. There will be 28 reaction control system engines on each Starliner service module. And finally, Stage 4 consists of the launch abort engines. These 40,000-pound thrust engines will separate the capsule and its service module from the rocket in the event of a launch or ascent failure. Each service module is equipped with 4 launch abort engines. If the launch goes smoothly, the propellant will be used to support mission operations. Let's take a look at the simplified process of how the Boeing Starliner should land. Step 1. The first step is undocking, during which the thrusters are ignited to ensure a safe separation corridor. A spacecraft then initiates an outbound fly-around. Step 2. In this stage, the departure and entry cover hatch closes, allowing for a smoother transition for re-entry. Step 3. Departure resumes and the spacecraft makes an approach ellipsoid exit, aligning with the correct thrust angle. Step 4. This step involves the separation of the service module, thereby reducing weight for re-entry. Step 5. The forward heat shield is jettisoned, allowing the drogue parachute to deploy. Step 6. At this stage, the main parachute pops out, significantly slowing down the spacecraft. The rotation handle also deploys, ensuring that the Starliner remains upright. Step 7. Additionally, the base heat shield is jettisoned, allowing the next steps to proceed smoothly. Step 8. What sets the Boeing Starliner apart from its predecessor is that it is designed to land on the ground instead of in the ocean. The solution involves deploying large landing airbags which protect the spacecraft from damaging when hitting the hard surface. This feature allows the capsule to be reused for future space missions, provided everything functions as expected.